In this video, we're going to continue our study of rotational motion. We'll build on the basic definitions for rotational quantities that we made in the last video and learn about rotational kinematics and rotational dynamics. Let's start with a review question. An object is moving clockwise and slowing down at the position shown below. What's the direction of the tangential acceleration, the radial acceleration, the total acceleration, and what component of the acceleration is related to the angular acceleration? Why don't you go ahead and pause the video and see how you do on this on your own, and then restart the video. Okay, so let's start out with, I think, the most straightforward of all these different accelerations, which is the radial acceleration. Remember that any time an object is going in a circle, there is always an acceleration towards the center. That's what we mean by the radial or centripetal acceleration. So it's on a radius towards the center. And again, when we talked about uniform circular motion, we called that the centripetal acceleration. So same thing. So if the object is going in uniform circular motion, that's the only acceleration there is. However, in this case, you'll notice not only is our object going in a circle, but its speed is changing. It's slowing down. We're told that the object is going we're told the object is going clockwise, so it's going around the circle in that direction. If it's slowing down, then there must be a component of the acceleration opposite the direction of motion. And in that case, then that direction would be this way. That's opposite the direction the object is going. Notice that that acceleration is tangent to the circle, and so we call that the tangential acceleration. Again, we only get a tangential acceleration if the object is either speeding up or slowing down in addition to going in a circle. If it's going with a constant speed, then we just have the radial or centripetal acceleration. We're then asked to find the total acceleration. Well, this is just vector addition. So I'll take my radial acceleration and I will add my tangential acceleration, and therefore my total acceleration is simply in that direction. Okay, so that's just a matter of drawing the two vectors for radial and tangential acceleration and then just doing our basic vector addition. Let's look at the next question. Which component of the acceleration is related to the angular acceleration? We defined angular acceleration, alpha, as d omega dt, the rate of change of the angular velocity. So the key thing to understand about alpha is in uniform circular motion, alpha is 0 because the angular velocity isn't changing. And that's why when we covered uniform circular motion, we only had the radial component of the acceleration. Therefore, you'll notice that alpha is related to the tangential acceleration. If the object's moving with a constant speed in a circle, there is no alpha, there is no AT. In terms of the relationship, it's that the tangential acceleration is equal to r times the angular acceleration. And I want to just point out another way you can kind of see that that makes sense. We have that the linear velocity is equal to r times omega, the angular velocity. Notice dv dt is a and d omega dt is alpha. So in other words, if you just take the derivative of this equation, you get the next equation. So the angular acceleration is related to the tangential acceleration. Objects going in with a constant speed, there's no alpha, there's no AT. We're just back to the simple case of uniform circular motion. Okay, so let's look at where we are in terms of our linear and rotational quantities. At the beginning of this course, we defined our linear quantities. position, displacement, velocity, and acceleration. And now in our last video, we've defined our rotational quantities: angular position, angular displacement, angular velocity, and angular acceleration. Notice that the definitions are exactly the same. Other than we're using different variables, the equations are identical. And that means that if we want to look at kinematic equations for rotational motion, all we're going to have to do is take our one-dimensional kinematic equations and change the variable names. So here are our kinematic equations. These are the equations that we derived back at the beginning of the course, and you'll notice that all I've done to come up with the rotational kinematic equations is simply swapped the variables. So instead of v is equal to v naught plus at, omega is equal to omega naught plus alpha t. Again, because we defined our basic quantities exactly the same way as we did for linear motion, then these rotational kinematic equations must also be true. Remember, though, that our linear kinematic equations are only valid if we have constant acceleration. And therefore, our rotational kinematic equations have the exact same constraint. We can only use them if alpha is constant. So if the angular acceleration is constant, then we can use these kinematic equations. Let's do an example to try out these kinematic equations. Remember, we looked at a hard disk problem in the last video. I gave you the frequency and you had to find out the angular velocity. So we'll continue with that problem. A computer hard drive rotates with an angular velocity of 754 radians per second. That's what we found in our last video. If it took 4 seconds for the hard disk to spin up to speed from rest, what was the angular acceleration? Well, just like any kinematics problem, you're going to get it right or wrong based on do you correctly identify what you know and what you don't know. So let's go through that. In this case, we're told that the hard disk spins up to speed from rest. Therefore, the initial angular velocity is going to be 0. The final angular velocity here is given as 754 radians per second. You'll notice we're also given how much time it takes for this change to occur. T is equal to 4 seconds. And we also see that what we're looking for is alpha, the angular acceleration. Once we've correctly identified what we know and what we're looking for, now you can look at those three equations and see which one you think is going to be the best one to use. Well, the best one is going to be omega is equal to omega naught plus alpha t, because that has everything we know and the one thing we don't know. Just like when we've done kinematics before, anything that's 0 we can go ahead and cross out, and then we want to solve algebraically for what we're looking to find. So alpha is equal to omega over t, or 754 radians per second divided by 4 seconds, which is 189, and that would be radians per second squared. Remember that the unit of angular acceleration is radians per second squared. And we can see that that makes sense because we've got radians per second over seconds. What was the angular displacement during this time? So once again, we want to make sure we understand conceptually what we're asking for. If you picture the hard disk spinning around, you can imagine drawing a line on the disk, and what we're looking for is what angle does that line go through during this 4 seconds where the hard drive is starting up. Just like in any kinematics problem, I can always pick my origin to be 0. So I'm going to say where the line starts is at 0. In other words, theta naught, the initial angle, is 0. The equation we want to use then is theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And what we're looking for is theta. What is that angle that the hard drive went through during these 4 seconds? In this case, we can get rid of theta naught, as we said. We also remember that omega naught is 0, so we get rid of that central term. And we now just have to plug in. So we get theta is equal to 1/2 times the angular acceleration of 189 times 4 seconds, and we got to square that. If you calculate that, you're going to get 1508. And what are the correct units for that? Well, hopefully you said radians, because since alpha is in radians per second squared, when we multiply that by time squared, we end up with just radians. So that would be the total angle that the hard drive spun through. Now, obviously, what that's telling you is it went through a whole bunch of revolutions during that time. That's our last question for the problem. How many revolutions did it make during this time? This is really just a unit conversion. In other words, we know that if we have 1508 radians, to convert that to revolutions, we just want to remember that in one revolution, there are 2 pi radians. And so, therefore, I can cancel out radians and radians, and I'm going to end up with revolutions. If you take that 1508 and divide by 2 pi, you should get 240 revolutions. And so that's how many times that hard disk went around in that first 4 seconds. You'll notice that what we're doing in this chapter on rotation is we're simply going through and following all the steps we went through when we were learning about linear motion. We defined our quantities, we did linear kinematics. Well, the next thing that we did was dynamics, in other words, Newton's laws of motion. And what we want to do now is see what is the equivalent for rotation. So what are the equivalents of force and mass? In other words, what does the angular acceleration depend on? We know that for linear motion, the acceleration is the net force divided by the mass. In other words, Newton's second law. Well, what we have for rotational motion is alpha, and we want to understand what does alpha depend on. Well, it turns out it depends on 2 things that we haven't really talked about yet. The equivalent of force for rotation is torque. And so a couple things, we use the Greek letter tau to represent torque. And so the quantity is called torque. And notice that it's the net torque on an object, just like the net force on an object for linear motion. The equivalent of mass for rotation is moment of inertia. And you may remember that I talked briefly about this in our first video on rotation, where we looked at the fact that the disk beat the hoop down the incline. And the reason that that occurred was because the hoop and the disk have different moments of inertia. So what we want to do over the next few slides is learn more about what is torque and what is moment of inertia. Well, let's start out by looking at torque. So if we want to get an object to accelerate, we know that we just apply a net force. The equivalent question is, how do we get an object to rotate? So imagine I've got some different wrenches here where I'm trying to tighten a bolt. And let me just propose some different ways I could use the wrench. Maybe I exert a force right here. So I put my hand kind of in the middle of the wrench and exert my force there, where the force is a distance r from the center of the bolt, the point of rotation. Now maybe instead I apply that same force at the end of the wrench, a greater distance away. Or maybe I exert a force at the end of the wrench, but I exert the force in that direction. Again, a distance r away from the pivot. Maybe I exert the force in the middle again, but I exert the same force, but now at some angle as opposed to perpendicular to R. So of those different options, which one of them is going to be the most effective way to tighten that bolt? What do you think? Well, my guess is that you picked this one because we've all either used a wrench or even just opened a door. You know, picture trying to open a door by pushing near the hinge versus far away from the hinge. So you probably all realized that that's going to be the most effective way to do it. Notice that in this case, the angle between R and F is 90. Now, in this case, you'll notice that's a really dumb case. I'm not going to do anything if I exert the force directly along the wrench. It's certainly not going to tighten that bolt at all. So the angle matters. And that's really what we learn about torque, that it's not just what force you apply, but where you apply it and at what angle relative to the distance from the pivot. So this would be completely ineffectual. These two would work, but not work as well, and this would be the best. If you've never seen the torque formula before, see if you can guess what the formula would be. Well, you'll notice that if you guessed that the torque is equal to Rf sine theta, you've guessed correctly. In other words, we know that in this case that would be an angle of 180. Nothing happens then. An angle of 90 degrees is the best, and angles between, that are less than 90 or greater than 90 aren't going to work as well. And of course, 0 and 180 don't work at all. So it makes sense that there's a sign in the formula. Also, it probably makes sense to you that the farther away you are from the rotation point, the greater the torque is going to be. And obviously the force, if we increase the force, the torque is going to increase. So the magnitude of the torque is given by that formula, Rf sine theta. Now it turns out that torque is actually a vector. That's just the magnitude, but that doesn't really tell us anything about the direction. Turns out that the torque is the cross product of R and F. In this course, we're not going to get into cross products, but in our next course we will, and I will talk more about torque at that point. For right now, we're just going to concentrate on looking at the magnitude of the torque. So if we want to calculate the magnitude of the torque, we just need to know R and F and theta. Let's take a look at the units of torque. You'll notice from the formula, torque should have units of meters times newtons, because obviously sine theta doesn't have any units. We don't give torque its own unit. So when we're dealing with torque, we usually just write the unit as Newton meters. Now, one of the important things here is you might be thinking back to the definition of a joule. A joule is also a Newton times a meter. But don't use joules for torque. And the reason for that is torque is not energy. So remember, the unit of a joule is a unit of energy. And remember that energy is a scalar. Torque is a different thing because it's a vector. And so don't use joules even though the units are equivalent. Always use Newton meters. Go ahead and pause the video and do this quick problem for me. A bolt on an engine needs to be tightened to a torque of 90 Newton meters. If the wrench is 26 centimeters long, what perpendicular force must the mechanic exert on the end of the wrench? So in this case then, R is 0.26 meters. And we're trying to figure out what perpendicular force F we need to exert on the wrench. So we know that theta is going to be 90 degrees. In this case, then, we can just take our formula for the torque, that the magnitude of the torque is Rf sine theta, and therefore F is the torque divided by R sine theta. In this case, then, we just have a torque of 90 divided by 0.26 times the sine of 90 degrees. And we get a value of 346 newtons. So that would be the force required to provide that torque. Remember that we're trying to understand the rotational equivalent of Newton's second law. And we've said that the angular acceleration is equal to the net torque divided by the moment of inertia. We've now talked about what we mean by torque, so now we have to talk about moment of inertia. Again, think of the moment of inertia as the rotational equivalent of mass. In that introductory question that I gave you in our first video on rotation, we looked at the fact that a hoop and a disc roll down the incline with different final speeds. And we said the reason for that is because the mass is not distributed in the same way. Therefore, moment of inertia has to have not only how much mass there is, but how it's distributed. Let's look at kind of the simplest case we have. Here is what looks like kind of a barbell, and that barbell is going to rotate around this axis. And so what we want to look at is, what is the moment of inertia for an object like that? If we have an object that's made up of discrete particles, then we can calculate the moment of inertia with the formula given here. So let me just kind of write this out to make sure you understand how to use that formula. Let's call the mass on this end m1 and the mass on this end m2. So we know that where the mass is matters, and specifically we're going to call this distance to the center of the mass from the rotation point r1, and we'll call this distance from the rotation point to the center of m2 r2. Therefore, what this formula is saying to do is it's saying take each mass and multiply it by the square of its distance from the rotation point, and then add that all together. Therefore, in this example, I would have m1 r1 squared plus m2 r2 squared. That's how I would calculate the moment of inertia for that object rotating about that central point. Notice that r makes a big difference because it's squared. So if you double how far away an object is, the moment of inertia would go up by a factor of 4. Now, what if we have some kind of continuous object like a sphere or a disk? In that case, you actually have to calculate the moment of inertia by doing an integral. Because most of you are in Calc 1, I certainly am not going to expect you to be able to calculate moments of inertia in that way. But let me just kind of talk about what does that integral represent conceptually. What that integral is saying is, think of this continuous mass m as being broken into tiny little pieces of mass dm. And if I could take that little piece of the disk and figure out its distance from the rotation point and square it, that would be that little piece of mass's contribution to the moment of inertia. So what an integral in this case represents is it just says break the object into a bunch of infinitesimally small pieces and then add up the effect of all of them. In Calc 2, you'll do problems just like this. But for right now, I'm going to give you some results in a minute that you'll be able to see what do these moments of inertia look like. Before we do that, though, let's do a problem involving individual objects. A 4 kilogram and a 3 kilogram mass are attached to either end of a light horizontal rod of length 1 meter. The point of rotation is in the middle of the rod. I'm going to label this mass as M1, so that's 4 kilograms. I've got mass 2 over here, which is 3 kilograms. We're told that the rotation point, and again, this barbell is going to be rotating around like that. We're told that the rotation point is right in the middle. So in other words, R1 would be 0.5 meters. And R2, so that's R1 here, R2 would also be 0.5 meters. And again, that's the distance from the rotation point to the center of the object. So you're asked to find the moment of inertia for the system, and then the second part is if the system accelerates from rest to an angular velocity of 12 radians per second in 6 seconds, what was the torque exerted on the system? Why don't you go ahead and pause the video and see if you can work through this problem on your own. Just to give you one hint, you're definitely going to have to use some rotational kinematics in the problem, as well as your definition of torque and definition of moment of inertia. Okay, let's go through the problem together. So the first thing we want to do is find the moment of inertia. We know that moment of inertia is the sum of each individual mass times its distance from the pivot point or rotation point squared. In this case then, I've got two objects, m1 r1 squared and m2 r2 squared. And so I can just go ahead and plug in the values to calculate that. So we've got a mass of 4 kilograms at a distance of 0.5 meters away, a mass of 3 kilograms, a distance of 0.5 meters away. And when you calculate that, you should get a moment of inertia of 1.75 kilogram meters squared. Notice the units for moment of inertia are kilogram meters squared. Again, that makes sense just because it's a mass times a distance squared. Okay, we're asked to find the torque on a system that caused an acceleration of this object from 0 radians per second up to 12 radians per second in 6 seconds. In order to figure out the torque, we know that the net torque is equal to the moment of inertia times the angular acceleration. Therefore, we've got to figure out what alpha is. In order to do that, I'm going to use kinematics. We see here that omega naught is equal to 0, that omega is equal to 12 radians per second. We see that this occurred in a time of 6 seconds. And therefore, since I'm looking for alpha, the equation that I want to use is omega is equal to omega naught plus alpha t. We can see that omega naught goes away, and solving algebraically, I get alpha is equal to omega over t, or 12 divided by 6, which is 2 radians per second squared. Once I've got alpha, then I can figure out what was the net torque that caused this acceleration. So I've got I times alpha, 1.75 times 2, and we end up with a net torque of 3.5 Newton meters. So that would be the answer to our question. Notice I could have asked a follow-up question. I could have said, if the force was applied, let's say at a distance of 0.25 meters right here at an angle perpendicular, then what was that force to produce that torque? And then we would use the definition of torque to figure that out. Now, I mentioned that to calculate the moment of inertia for different solid objects requires the use of integrals. So again, I'm not expecting you to be able to do that. Let me give you what the moments of inertia are for three common types of rolling objects. If we have a solid sphere that's rolling along, then it has a moment of inertia of 2/5 mr squared, where r is the radius of the object. Okay, so that's what r is in all of these cases. If I've got a ring or a hollow cylinder, or what we called a hoop, in the first video on rotation, it would be mr squared. And if it's a disk or solid cylinder, it would be 1/2 mr squared. Notice that a couple of these things make sense conceptually. We've said if you just have one object, a distance r from the rotation point, that the moment of inertia is mr squared. Well, think about this ring or hollow cylinder. All of the mass is at a distance r from the center. So it makes sense that I is equal to mr squared. The other thing you'll notice is now we understand why our disk beat our hoop down the incline, because the moment of inertia for a disk is half as big as the moment of inertia for a ring or a hoop. In our next video, we're going to continue with this, and we'll look at how we can use conservation of energy with what we've learned about moments of inertia to actually determine what the velocity would be for a hoop or a disk rolling down an incline.